Okay, so thank you very much. I guess you can see my screen and hear my voice. So it's a great pleasure to participate to this event. And of course, thank to the organizers for making this happen despite the situation. And as a member of the science community, I've also been extremely saddened. I'm shocked by the tragic news about Elizabeth Meckes. In my talk, there will be a part concerning Stein's method, to which Elizabeth contributed quite a lot. So I will quote her at a certain point. So the title of my talk is some application of variational techniques, so like variation inequalities of the type, for instance, Poincar inequality, to problems in stochastic geometry. And a specific focus I would like to put on my lectures is on geometric quantities and geometric structures that are related to random point configurations, and so in particular to Poisson random point configurations in the plane. So my talk will be divided in three parts. There is a first part that do not correspond exactly to the three lectures. So there will be a first part where I will introduce what a Poisson measure is, and I will describe some of the techniques that we use that are connected to some discrete formula of integration by parts. And then I will present to you a result that is a sort of prism through which I'm going to present the results of my lectures, which is the Poincar inequality on configuration spaces, and some of the refinements that are available on the Poisson space, that is like the L1, L2 inequality or OSSS inequality. And then the centerpiece of my presentation will be part two, where I will present how one can combine a certain probabilistic techniques, which is known as Stein's method, which with another technique, which is known as the Maldivian calculus of variation, in order to obtain explicit probabilistic approximations. That is, results that measure the distance between the distribution of two random elements, a bit in the spirit of the variance theorem. And the connection with the theme of the trimester and the theme of the school, apart from the fact that I'm dealing with an infinite dimensional object as a Poisson random measure, is that the kind of bounds that are connected with part two so allow to typically are expressed in such a way that they present an analytic dependence on dimensional parameters. So one can keep track of the dimensional parameters in the bounds through explicit constants. And also the kind of probabilistic approximations I'm dealing with extend quite naturally to the multidimensional setting. So approximation of random vectors by random vectors. And also in this case, the bounds are such that the dependence on the dimension of the vector appears explicitly in the bounds. Okay, so there are at least three connections with this notion of high dimensional probability. And then there will be a third part, but of course, it really will depend on time, where I will present to you results that do not use the Poincar inequality. So part of the results that I will present are obtained via Poincar inequality. In some situation, this is not applicable, and therefore I will tell you what to do if time permits. So all this is connected to a number of joint works. I'm not reading the list, at least the list will be put online, and therefore, but some of the people that have contributed to this part of my research are in the audience and are also among the organizers of the trimester. Okay, so I will start therefore. So my focus therefore will be on functionals, and in particular functionals with the geometric flavors that are associated with a Poisson random measure. So I will start with the basic definition of what a Poisson random measure is for me. So my notation will be always the same. Omega fp is the underlying probability space. I will denote expectation with E. And I will consider a point measure, so Poisson point processes that are defined for the moment on a general space. So in my application, the space will be always of the form RD, Euclidean D-dimensional space cross Cartesian product something. But so in this case, in this general presentation at the beginning, we can take as a reference space, a Polish space A, which is endowed with its Borel sigma field. And on this space, I'm considering a measure, which is deterministic non-atomic positive measure, which is locally finite. And locally finite means that this measure is finite on bounded sets. Okay. Then the kind of random object I'm considering is a random object that takes values in a space that I'm going to denote by N of L, which is a space of locally finite measures denoted by mu, that take values in the integers and possibly take also the value infinity. So this space of locally finite measure is endowed with a sort of canonical sigma field. And so at the end of the day, I'm defining one of the main objects of my presentation, that is a Poisson random measure with intensity lambda on the Polish space A calligraphic, to be a random element with value in this space of integer valued measures. So this is therefore a collection of random variables that are indexed by measurable sets with the following property. If you fix a measurable, set, then the random variable E of B, which is the mass that is put on the space on the set B by the Poisson random measure, by this random measure, is a Poisson random variable with parameter lambda of B. And if I consider a collection, an arbitrary collection of disjoint random sets disjoint sets B1, Bn, then the random variable eta B1, eta Bm are stochastically independent. And in my definition, I have just extended the definition of a Poisson random variable to the whole spectrum 0 infinity by implicitly declaring that the Poisson random variable with mean 0 is just the 0 random variable, and the Poisson random variable with parameter infinity is just the infinity random variable, random variable which is equal to infinity with probability. Okay, so this is my definition of a Poisson measure. Now, some remarks that will just put forward the geometric content of this definition are the following. So, okay, the first remark is that this kind of object in this generality exists, so one can explicitly construct this kind of object. Then another remark is that since we are working on a Polish space, then every locally finite measure that, that is integer valued is actually the form of a sum of Dirac masses, possibly infinite sum of Dirac masses. And one typically refers to the centers of these Dirac masses as the support of the measure. Okay, so this will be what I will denote as the support of the measure. And then another result is that since lambda is non-atomic, then with probability 1, every singleton in our underlying probabilities Polish space is charged by the Poisson measure either with probability 0 or with probability 1. There are no double points, triple points, etc. So this means in particular that every probability measure, every Poisson measure, the one that I defined in my previous slide, can be identified with its support. So all the information about the measure is contained in this set of points that are contained in the support of the measure, because there is no additional mass that is put on each one of the points. And this is why a Poisson random measure is typically used as a probabilistic model for a random point configuration. Okay, so this is, you can identify this object with its support. The support is a collection of points in the Polish space, and therefore one can identify a Poisson measure as such as the one I just defined as a collection of points that are randomly displaced on the Polish space A calligraph. And then if you identify A with RD, then you have a random collection of points in the Euclidean space. And according to the intensity measure, lambda, that you choose, then these points will be more or less uniformly distributed in the space. So just one point is that actually the existence of Poisson measures is not very difficult to prove. For instance, if you have an intensity measure which is finite, then one can explicitly build a Poisson measure as follows. Just take a random variable P, which is a Poisson random variable with parameter given by the total mass of the measure lambda, and then define a random measure eta by taking the sum from 1 to P of Dirac masses that are centered on IID random variables, on a sequence of IID random variables that are all distributed according to the measure lambda normalized by its total mass. So a simple computation shows that this is exactly a Poisson measure as the one that I just defined in the previous slide. And then starting from that, you can just check the two properties of independence and of the fact that the measure eta of each set is actually a Poisson distributed. Okay. So this is just some notes. And if you consider lambda as a sigma finite measure, then you can just take a partition of your space into subsets of finite measures. And then on each of in each of those sets, you can just apply this construction and then glue everything together. So this is just an object that exists, and it can be explicitly constructed in terms just of independent random variables and then an independent number of points that are Poisson distributed. So there is a book that I love very much, which is by Gunther Last and Matthew Penrose, that are lecture notes on the Poisson process. And this is a very beautiful book, and it contains all the details even in much more generality than just Polish spaces, just for general spaces. Okay, so this is my main object. Okay, so now let me give you some example of a Poisson measure that is relevant in stochastic geometry. Okay, so one typical example of a Poisson measure that I will refer to during my lectures is given by a Poisson measure that generates one of the favorite models for stochastic geometers that work with random point configuration. And this model is known as the Boolean model. And in some form, it was introduced in 1959 by Gilbert in the context of telecommunication. So this object is obtained as follows from the previous from my previous slides. So you take as just reference space A the product space of a Euclidean space Rd, and then a space M, which is just, let's say, the class of compact sets of subsets of Rd, such that the origin is contained in the interior of K. And you call this space the space of grains. Okay, the community calls this the space of grains. Then you take a Poisson measure, which is on this space, on this product space. And for intensity, you take just the product measure, which is given by some multiple gamma of a Lebesgue measure on Rd, cross a probability measure on the class of compact sets, right? And this probability measure, in this general definition, can have any form, and then there are several restrictions that actually allow one to make computations. Okay, so since the Lebesgue measure is non-atomic, then this measure here, lambda, is also non-atomic. So this means in particular that we can, by my previous remark, that we can identify our Poisson measure eta with a collection of points that are actually given by pairs. Each pair contains a location in Rd, the red one, xi, that is here, and then a compact set that contains the origin, right? And this in an infinite number. And what one calls the Boolean model is a random subset of Rd, which is obtained by taking the union of all the compact sets that are obtained by taking the ith compact set Ki, and then by translating it in the direction xi, okay? So in this particular speaker's artistic impression of the Boolean model, so you see that, so the red points are the location in Rd, and then for each one of the points, I have, each one of the points is surrounded by blue area. And this blue area is exactly the compact set Ki, which is recentered on the point xi. Okay. So this is the case for d equal to 2. It is one of the most popular constructions of a random subset of a Euclidean space. One important remark is that if you take for Q a trivial configuration, that is, if you assume that Q selects with probability 1, so it is equal to the Dirac mass in balls, which is centered on the ball with radius 1/2 that is centered on the origin, then the Boolean model actually encodes what one calls the Gilbert graph. And so the Gilbert graph is obtained as follows. So you take as vertices the red point of the Boolean model, and then each red point is surrounded by a circle with radius 1/2. And the Gilbert graph tells you that you connect 2 points x and y, 2 points, red points x and y, if and only if the Euclidean distance is less or equal to 1. And this is the same, of course, as having that, saying that 2 points are connected if and only if the disks around them in the Boolean model are superposed, so overlap in some form. Okay. So this is one of the most basic models of random geometric graph, which is encoded in the Boolean model, which is a model of a random subset of RT. And so, as I was anticipating, my principal goal is to tell you something, to describe to you some techniques that are useful for dealing with variances, with covariances, and with second order fluctuations, like for instance, central limit theorems for random variables that are given by some measurable function of my underlying random point configuration. Okay, so this is one of the this is the principal goal of what I would like to tell you. So you can hear me, right? Because my configuration doesn't allow to see anyone. You can hear my voice, right?
Yes, yes.
Okay, good. I don't see it, just black screen, so the old fear of speaking in the void is there. Okay, so some example of these random variables are, for instance, the following of the kind of problems one can deal with. And actually, I'm going to present to you two problems that are really very different, and I will explain to you in which sense they are different. So typical examples of geometric quantities that can be studied with the techniques I'm going to present you are the following. So the first one are quantities that are related with what one calls counting or related to counting statistics that are associated with the Gilbert graph. So for instance, you can do the following. You consider the Gilbert graph that I just defined in my previous slides. And then you take the restriction of the Gilbert graph, that is of the vertices of the Gilbert graph, to some window W, like this one. And once you have the restriction of the Gilbert graph to a window, you can count things. So for instance, you can count the number of edges. Here are 1, 2, 3, 4, 5, and 6. You can measure the length of the graph within the window, something like this. Or you can count the number of triangles. There is one triangle, or the number of arcs like this one. There is one of them, two of them here, and squares, etc., etc. And you can ask yourself what's going to happen is that if I let the window, the size of the window diverge to infinity, and at the same time, if I let the dimension, for instance, go into infinity. Okay. So you have, this is just a random quantity, and then you let some relevant parameter like the size of the window or the dimension of the underlying space go to infinity. And then you say, okay, what are the fluctuations of this random variable in the limit for W diverging to the whole space, for instance, or the dimension diverging to infinity. Okay, so this is a typical example of a collection of random variables that are called U statistics. And things are quite easier, not easy, but easier for U statistics than for random variables that are not used. So what is a U statistic is something that can be represented as a sum of a finite order over, let's say, over vectors of points in the support of the Poisson measure. But I will define this later on, maybe. I don't need the definition right now. And then what I want to tell you also is that really an enormous motivation for developing tools for controlling the variances of random variables. And in particular for random variables that take values in a discrete set like 0, 1 of minus 1, 1 comes from percolation theory, of which I'm not an expert, but that I am very interested in. And for instance, so a typical random variable that emerges in continuum percolation, in model of continuum percolation is the following, is for a fixed n. So I consider a random variable, which is the indicator of an event that I'm just representing here with the usual symbology of percolation theory, but this is just the event that it is possible to travel from the origin, which is here, to the boundary of the ball with radius n by just crossing regions that are occupied by the Boolean model. Okay, so I can go from here to here, on from here to here, by just crossing the Boolean model. And so this is an event that can happen or cannot happen according to the configuration of the Boolean model. And if one let n, which is the radius of the ball, diverge to infinity, then this, so I didn't write it, but this is the limit for n that goes to infinity, then one obtains a crucial quantity in percolation theory, which is what is called the percolation probability. It is the probability that there exists an infinite component of the Boolean model that contains the origin. And so controlling the variance of quantities of this type is quite a big business in percolation, continuum percolation theory, and inter-theorem random graphs. Controlling the variance of and the fluctuation of objects of this type is also a very important topic. And the situation is quite different because this guy here is not a U statistic, and actually is basically the opposite of a U statistic in a sense that I will describe to you later. Okay, so these are like two geometric quantities, families of geometric quantities that motivate the study of fluctuations of random variables that emerge in a geometric constant in that context. And then, of course, I'm representing everything on the plane, but these models are in RD, on Euclidean spaces, and there are many things to understand concerning dimensions, especially for percolation theory. Okay, so this is my motivation. So now my point of view will be, as is explicit in my title, is to control the fluctuation, in particular the variances and second order results for quantities of this type by using variational inequalities on the Poisson space. And the way I do it is that I want to build on the Poisson space a family of operators. These are not really differential operators because we live in a discrete space, but a sort of difference operators. And these different operators allow one to then establish variational inequalities that can actually be applied to geometric problems. And one very nice collection of tools that allow in many situations to establish differential inequalities or variational inequalities are those that are related to integration by parts formula in general. Like the Poincar inequality on the Gaussian space can be proved by implementing integration by parts and then Jensen in some form. On the Poisson, and when one deals with infinite dimensional objects, all these techniques that allow one to deduce differential inequalities by using integration by parts formula are covered by this big umbrella. This is known as the Maldivian calculus of variation. So Maldivian calculus is a theory, was introduced in the 70s on the Gaussian space by Paul Maldivian, motivated by the problem of regularity of solution of stochastic differential equation. And then this theory has extended to other spaces, so in particular to the Poisson space. And this is what I'm going to present to you in a sort of a succinct form. But what I want to tell you is the following. When one studies this Maldivian calculus of variation on a Gaussian space, so this is typically presented as a theory that allow one to control and transform covariances between random variables. And this is typically presented as an L2 theory. So it's a theory where you can actually control the inner product between square integrable random variable or random elements that let's say, take values in some L2 space or in some Hilbert space, which is the right way of looking at the Maldivian calculus, at least at the preliminary stage. When one moves to the Poisson setting, then of course you can build the Maldivian calculus operators integration by parts by using L2 formulae, but everything that is needed in order to develop the right formulae are actually L1 inequalities. So my message for you is that Maldivian calculus on the Poisson space, as I'm going to present it to you, is an L1 theory as these guys. And the reason why I tell you that it is an L1 theory as these guys is that everything that I'm going to tell you later on about Poisson processes and integration by parts formula can be basically deduced by just one identity. And this identity is known as the Mecke formula. So Mecke formula comes from the 70s. And it's a formula that tells you the following. So consider, so it's a formula that involves integrals with respect to the Poisson measure eta of random functions. So the formula tells you the following. So consider a function h, which is actually two variables. So it depends on the space, on points in the space A, and also on the configuration, on the random configuration given by the Poisson process. It is here. And consider the integral over the whole space with respect to your Poisson measure eta on the function h, which depends on x, and depends on the Poisson process eta, and take the expectation of this guy. And the Mecker formula tells you this is the same as taking the expectation of the whole space A of the deterministic control measure or intensity measure lambda of the function h, where now the dependence on eta has been replaced by the dependence on eta plus a Dirac mass. So a Dirac mass has been added to the random point configuration. And okay, there is a form where also you can remove a mass, which is this one, but I'm not going to comment on this one. But this is all. This is a Mecker formula. And actually, this Mecker formula tells you several things. So first of all, this is the formula that characterizes the Poisson process in some form. So among point measures that verify some specific requirements. And also, it tells you that at the heart of all the formula I'm going to tell you, there is this basic operation that consists in taking your Poisson point process and in adding one point to the support of the Poisson process. Okay, so all the formula that have analytic flavor, in principle, that I'm going to present to you in the next slides, are actually based on an operation which is a very precise geometric meaning. That is, you have a random point configuration, you build some quantity around it, like for instance, a random graph, and then you add one vertex to the graph, and you see what happens. So it will create some edges. In some graphs, will destroy some edges. It will add some points to your Boolean configuration. But so this is something that can be really described geometrically. And so this also implies that on the Poisson space, this in principle abstract Maldivian calculus can actually be interpreted all the way in a very simple and appealing geometric manner. So let me also tell you that this Mecker formula, this formula here, if you reduce it to the simplest situation, which you have just one-dimensional Poisson random variable. So in the one-dimensional setting, where just one Poisson random variable, so the Mecker formula can be seen as an infinite, actually is an infinite dimensional version of the fact that if you have a Poisson random variable, so you have Poisson random variable which is distributed as a Poisson one-dimensional random variable, so integer value with parameter x, then the expectation of x, let's say phi of x, for every function phi, let's say bounded phi, is equal to gamma, the expectation of phi x plus 1. Okay, so this is an elementary computation. You can just write this two guys as a series and check that they are the same. And actually what happens is that since the Poisson measure is characterized by the moments, this also goes in the other direction. So it is a characterization of the Poisson distribution. And this is one simple statement of what one calls the Chen-Stein lemma, which is also relevant in geometric applications. Okay, so but thing is, on the Poisson space, most of the relations that are relevant for my lectures can be derived just by an application of Mecker formula, which is an L1 and L1 theory, and that also characterizes the Poisson measure among other point measures on the space A. Okay, let me go on. So let me tell you some operators that are, so I write Maldivian calculus here, but okay, I'm not probably respecting Paul Maldivian that never did anything with discrete objects. And I actually think he disliked quite a lot everything that was not related to some Gaussian structure. But this is how I call it. So this is Maldivian calculus as extended to the Poisson space. So there are several operators that are relevant in this setting. So one operator is this what one call the add one cost operator. So the add one cost operator basically appeared already in the previous slide, and it is just a run. So it should be centered around the point x and around the point x here. So, and it is simply the random variable that is at the point x. So it is simply the random variable that is obtained by taking a random variable depending on the Poisson process eta, and then by adding one Dirac mass to the support of eta, and then by subtracting the original configuration. The original value of the random variables is the add one cost, is the cost of adding one point to the support of your random configuration. And of course, without any surprise, the remove one cost operator is just the operator that takes a random variable depending on eta and subtracts the value of the same random variable whenever one deletes 1 point from the supportive field. Okay, so these are two typical quantities that have, as I was telling you before, a very precise geometric mean and geometric way of interpreting. Now, what happens on the Poisson space? I mean, the fundamental, you will see probably also in the next set of lectures, and in any case, many theories that are connected with functional inequalities. In many cases, everything can be encoded via the action of a certain semigroup on this random variables. And as on the Gaussian space, and a crucial object is given by what one calls the Ornstein-Uhlenbeck semigroup on the Poisson space. Okay. So if one understands the action of the Ornstein-Uhlenbeck semigroup, then all the other relations and the prominent role of certain quantities becomes quite evident. And so the Ornstein-Uhlenbeck semigroup on the Poisson space is defined as follows. So first of all, maybe some of you I mean, I'm sure that some of you, but maybe a relevant part of the audience is acquainted with the Ornstein-Uhlenbeck semigroup on the Gaussian space. And the Ornstein-Uhlenbeck semigroup on the Gaussian space can be defined by a formula, which is known as the Mailer formula. And so this is actually how I'm going to present to you in this, is in a form which is called the Mailer form. Okay, and so the Mailer formula is a formula on the Gaussian space that expresses the Ornstein-Uhlenbeck semigroup in terms of the convolution of two rescaled copies of your original Gaussian object. Okay, and this rescaling, so in the Gaussian setting, rescaling a Gaussian element or rescaling a Gaussian random variable means just multiplying it by some constant. So you rescale because Gaussian objects are stable with respect to multiplication by constants. But now,
Giovanni, I don't know if you see the chat. There is a question by Mark Woolson.
I'm sorry.
Oh, so the question.
I don't see it because of my configuration, yeah.
So Mark asks, do we have to add a condition that X is not in the support of eta for add one cost operator?
The answer is that you can or you cannot, because the points that are in support of eta have Lebesgue measure, I mean, have lambda measure 0 in general, because it is not charged, it doesn't charge the singletons. And in all the formulae, this add one cost operator are going to be integrated. So it doesn't play really a very important role, but my definition is quite general. So it's not, you can choose whatever is more appealing to you. Because I mean, my random measure eta lives in a space where multiple points are allowed. So you can add a point, but this will not impact the formula because it will be integrated out with respect to a measure that gives mass 0 to that specific point. Okay. Does it answer the question?
I guess so, yeah.
Okay, good. Thank you.
Yes, thank you.
Thank you for the question, for following. So I don't know how to do it anymore, but okay, no. We use WebEx in Luxembourg, so I'm a bit clumsy with this. Okay, so now if you want to define the Ornstein-Uhlenbeck semigroup on a Gaussian space, then you have to use the rescaling properties of Gaussian measures of Gaussian fields. And in a Poisson setting, you cannot just multiply a Poisson measure by some constant. It doesn't make any sense. You just go out of your integer value setting. And actually what happens is that on a Poisson space, on a space of Poisson measures, the equivalent of rescaling is an operation of thinning. Okay, so this would call an operation of thinning. And so how I define it? So you fix t bigger than 0. And then for every t bigger or equal to 0, you define the eta e to the minus t thinning of eta, which is obtained as follows. So you start with the representation of your Poisson measure as a random sum of random Dirac masses. And then you thin this object in the following way. You multiply each one of the Dirac masses by an independent binomial random variable. everything is independent of everything, with a probability of success equal to e to the minus t. So if the binomial random variable is 1, then you keep the point. And if the binomial random variable is 0, then you delete the point from your random point configuration. Okay, so this is a thinning, of course, because you take away some points. And then in the same notation, let's add the following object, which is eta superscript t, which is an independent Poisson measure with intensity lambda as eta, but multiplied by factor 1 minus exponential of minus eta. Okay. And then one has the following. So one can prove actually that eta of t, that is the thinned measure, is a Poisson measure with intensity exponential minus t times lambda. Okay. And now, since if you sum two independent Poisson random measures that are the result is a Poisson random measure with an intensity which is given by the sum of the intensities. This is something that one can prove. One has that the sum of the thinned Poisson measure and the additional independent measure with intensity 1 minus exponential of minus t is actually the same distribution as the same distribution as the original Poisson measure eta. And this is the same as saying, it's the same operation that consists in you take a Gaussian random variable, a Gaussian random vector, and then you take an independent copy. You do something like this, G prime. So you take this linear combination of two independent copies of the same random vector G, and this has the same distribution as the original G. And this comes from the scaling properties of the Gaussian measures. And this is basically the same phenomenon, but where thinning is involved and not scale. So here there is another artistic impression of the Ornstein-Uhlenbeck semigroup. So you start with the black configuration, which is the black points here, here, and here. This is your original measure. Then each point is not removed with probability exponential minus t. So the non-removed points are the red ones. The other one are all deleted from the configuration. And then you add an independent points with an intensity 1 minus exponential of minus t multiplied by lambda. And what you obtain is a random object that has the same distribution in your original eta. Now the Ornstein-Uhlenbeck semigroup is therefore defined as follows. You take it defined, so it's a family of operator that acts on random variables and depend on the Poisson random measure eta as the expectation of f of eta t plus eta superscript t. So this is the object I define, and then you condition by eta. And if you look at the Gaussian space, we can even write the Ornstein-Uhlenbeck process on a Gaussian space. So if you have something that depends on a Gaussian field, this is just the exponential of f exponential of minus tg plus square root of 1 minus 2t g prime conditional on g. Okay, so this is the Ornstein-Uhlenbeck on the Gaussian, on a Gaussian space, where the scaling operation has been replaced by the thinning operation. Okay, so this object is like crucial. The properties of this object explain most of the things that one can do and one cannot do, at least by certain techniques on the Poisson space. So there is a direct connection with, I guess, the next series of lectures about the concentration of measures. And it is that this Ornstein-Uhlenbeck semigroup on the Poisson space, differently from what happens on the Gaussian space, and differently from what happens on the discrete hypercube, this guy here has the bad behavior of being non-hypercontractive. So I'm not going to define or use hypercontractivity for now, but there is a whole beautiful theory by Cri-Henry that tell you that if you have a non-hypercontractive semigroup, then you have no log sub F inequality. And so this means that you have some modified form of log sub F inequality that I think are going to play a role in the next series of talks. So I'm not touching that. I'm not going to log sub F inequality, but this is really the object that that explains many of the phenomena or the limitations of on a Poisson space. So now to conclude, for my last 6 minutes, I will tell you that what is actually fundamental for all the applications I'm going to develop is the description of the eigenspaces of this semigroup on the Poisson space. And these eigenspaces are one of my favorite topics, which is the Vineyard chaoses. So the eigenspaces of the Ornstein-Uhlenbeck semigroup on a Poisson space are the Vineyard chaoses, what one calls the Vineyard chaoses on the Poisson space. So I'm going to describe to you what they are. And I'm going to hint at some proofs, but of course it's a bit technical, not difficult, just technical. And I want to just explain to you something which is more substantial. So for every integer q going from 0 to 1, 2, etc., so we define the qth Vineyard chaos associated, which is also qt, to the Poisson measure eta in the following way. So C0 is just the space of constants. And then for every q, CQ is the L2 closed space of random variables that have a very specific form. These are multiple integrals, multiple Vineyard eta integrals actually, for the q of deterministic and symmetric kernels U integrated with respect to the compensated measure, which is given by eta minus L. So you take the original Poisson measure, you subtract the intensity, you integrate q times over the product space. And since you are dealing with discrete objects, you have to be very careful about the fact that you don't have to touch diagonals, okay? So this means that you have to exclude diagonals from your computations. So building objects of this type is not very difficult. You start from U with a simple integrand. For instance, you can take an integrand U that is just a linear combination of product of indicators of disjoint sets. And then you define in the usual way, because this is just, you define a multiple integrand in the usual way, and then you go to the limit in some probabilistic sense, exactly as you build multiple. So the only thing that is important for us are a few properties of these guys. So the first property is a philosophical property, which is not a philosophical property, but it is a remark that I'm not going to substantiate with a proof, is that these objects here are infinite dimensional analogous of Charlier polynomials. And we know that Charlier polynomials are the orthogonal polynomials for the Poisson distribution. You can actually, if you take simple forms of the integrands, like for instance, this one, then these guys are actually multivariate Charlier polynomials. And then you can go to the limit. But the connection with Charlier polynomials is less satisfying than the connection between multiple integrals on a Gaussian space and Hermite polynomials, but they are there. You can really look at them as infinite dimensional polynomials, or for the Q orthogonalized, as you do for Hermite polynomials for the Gaussian distribution. And they actually behave like polynomials a bit, because if you take a multiple integral for the Q and you multiply it by multiple integral for the P, then what you have is a multiple integral for the Q plus P. As if you take a polynomial of degree Q and you multiply it by polynomial degree P, you have a polynomial degree P plus Q. So they actually behave algebraically as polynomials, and they are built starting in some sense from polynomials. So the key proposition with which I will conclude my first part of the presentation is that these guys actually describe the action of the Ornstein-Uhlenbeck semigroup in the following, and have additional properties that are important. So what they do is the following: they're actually the eigenfunctions of the Ornstein-Uhlenbeck semigroup. So if you let the Ornstein-Uhlenbeck semigroup act of a multiple integral of order Q, then this gives you back the same multiple integral multiplied with the exponential of minus Qt. It's a bit of a computation. It's not very complicated by using properties of conditional expectations and then the definition of the Ornstein-Uhlenbeck semigroup via the Miller formula. And then one can also prove, as exactly as one proves Ito isometries on the Gaussian space for Ito integrals, you can prove that if you take two multiple integrals, one over the Q and one over the P, of kernels U and kernel V, then this expectation is equal to 0 unless the order P is equal to the order Q. And in this case, the covariance between the two guys is Q factorial multiplied by the inner product of U and V. Then a third property I will quote before finishing is that there is what one calls a Vineyard chaos expansion. So this means that exactly as for Hermite polynomials for the Gaussian distribution, or for homogeneous sums for functionals of independent random variables in +1, -1, for instance, then you can represent every random variable, which is a function of the Poisson random measure, as an infinite sum of multiple integrals, which one expresses in a functional analytical way as the fact that L2 is the direct sum of the Vineyard chaoses. And one last thing is that these Vineyard chaoses behave very well because if you apply to them the add one cost operator I was describing before, then simply by reasoning on the definition as an integral, you can see that this is obtained by just removing one order of integration, letting the variable x live free, and multiply by q. It's a very simple combinatorial computation, so the nice one. But apart from these four properties, I cannot tell you anything, and plus the multiplication formula, I cannot tell you anything that is remotely as appealing as for multiple integrals for a Gaussian, with respect to a Gaussian field. So we have all kinds of properties for multiple integrals with respect to a Gaussian field. They have moments of all order. All LP norms are equivalent to the topology of convergence in probability, and you concentration estimates of every kind. So all this fails miserably on the Poisson space. Actually, you don't even know, these objects are defined as objects in L2, but then you don't even know if they have moments that are higher than 2. Actually, in many cases, they do not have, and so on and so forth. So this is the fundamental object that describe the action of the Ornstein-Uhlenbeck semigroup. And then starting from that, I will introduce tomorrow some other operators, and then I will finally go to the Poincar inequality and to applications that are connected once again to geometry. So we have maybe 2-3 slides more of abstract reasoning, and then we will go back to something which is more amusing to describe. Okay, so thank you very much. Thank you very much.